Today, we are going to discuss ray tracing and its impact in the whole gaming industry. Before you click away, you need not know anything about ray tracing or anything about computer graphics in general. You need not even be a software engineer to see this video. I'm gonna demystify ray tracing as if you know nothing. When people see the term ray tracing, they feel like there is a lot of complexity involved in this. There is some technical wizardry involved in the whole ray tracing. No, ray tracing is rather simple concept. As we go deeper, the complexity comes with the cost of computational intensity. If you don't understand what exactly I mean, it's fine. I'm gonna explain everything about ray tracing. By the end of the video, you're gonna understand exactly what I mean. In this video, first we're gonna see what exactly is rasterization and how are computer graphics rendered on the screen. And then I'm gonna tell you how exactly lights were calculated before ray tracing was a thing. And then we're gonna talk about the ray tracing and how exactly does it work. And then I'm gonna discuss some drawbacks of ray tracing, and then I will tell you two techniques which are used by different game studios and different gaming companies to solve these problems. Let's go back in time to early 90s where games used to look very flat and the lighting used to look very off. Games generally use a technique called rasterization to render the scene. What exactly is rasterization? All rasterization does is take the whole 3D scene, that's a 3D frustum, and then present it to a 2D flat image that can be presented in our monitor. So all rasterization does is take the whole 3D scene and then converts it into a 2D image that can be presented to our monitor. That's it. That's all rasterization is. By default, rasterization doesn't take care of lighting. We can write a shader that can go through all the lights and then it can calculate approximate illumination to the surrounding objects of the light sources. But again, it's an approximation and it doesn't even calculate indirect lighting. Then how are lights calculated before ray tracing was a thing? In 1996, Quake came up with a technique called light maps, and many games after that used light mapping. I'm not gonna go what exactly is light mapping because that's not the point of the video. But there were many more techniques such as light mapping. There is cube mapping, and also there is probe based lighting, and there were many more techniques. But all those things approximate the lighting, but they are not accurate or they are not realistic as ray tracing is. So let's get into the main part of the video. That's the ray tracing. Ray tracing was first introduced in 1986 and was deemed to be impossible to implement. But why is it impossible to implement? All the games now are using ray tracing, right? To answer that, we need to know how exactly ray tracing works. Let's say we have a 3D scene. I need to illuminate the whole scene using ray tracing. All I'm going to do is I'm going to shoot a single ray from pixel forward, and that ray goes and hits some 3D object, right? And from that hit point, I'm going to shoot rays to each of the light source. These rays are called shadow rays. And then using the light intensity, light angle, normals, and many more stuff, we calculate the light at that particular hit point. That's direct lighting sorted. How exactly is indirect lighting calculated? So from the same hit point, we're gonna shoot each ray to all the surrounding objects. This is called one bounce. So from that particular hit point, we again shoot each ray to all the light sources. And again, light intensity is calculated at that particular point. And this happens for multiple bounces. That's it. That's all ray tracing is. Instead of shooting from one pixel, shoot rays from all pixels and you'll get the whole scene illuminated. Ray tracing seems very simple, right? What's so complex about it? To answer that, let's do a small calculation. Let's say I'm shooting 8 rays per pixel. There are 8 light sources in the scene, and let's say I'm calculating ray tracing for 8 bounces. Let's say we are playing a game at 1080p. Let's not even go for 4K. Now the total number of rays per frame here is the resolution multiplied with total number of light sources multiplied with total number of rays per pixel multiplied with number of bounces. If we calculate this, it would be nearing to 1 billion rays per frame. If we are playing a 60 fps game, we need 60 billion rays per second. Now you see why exactly I mentioned the term computational intensive. Gaming needs real-time ray tracing. We need to do it at the rate of 30 or 60 per second. How is this possible? First game that came out with real-time ray tracing is Battlefield 5 in 2018. It's crazy how it took 40 years to implement ray tracing after its proposal. There are many techniques that made real-time ray tracing possible. I'm going to explain two of the most important techniques. Bounding volume hierarchy, or BVH in short. Our whole scene is wrapped inside a cube, and the cube is divided into two cubes, and each cube is again further divided into two cubes. When a ray is hit from the pixel, it hits the outer bonding volume and then it goes into inner bonding volume. And if it hits the inner bonding volume, it goes further or it just stops there. Essentially, we are performing binary search here. By doing this, we are not allowing unnecessary rays to travel in the scene. This significantly reduces the number of rays in the scene. And the second technique I'm going to explain is green space ray tracing. Cyberpunk, released in 2020, uses this technique. Basically, our whole scene is rasterized into a 2D image, And then along with the rasterized image, a depth map and also a normal map are used. You need not understand what exactly depth map and normal map means. Using all these three textures, a new scene is formed, which has the geometry only visible to the screen. This is called a screen space. Now the ray tracing is performed in the newly created screen space. This will avoid our rays hitting unnecessary geometry. Whew, that's a lot of information to consume in one sitting, right? But that's ray tracing simplified. There are much more advanced techniques that are used in ray tracing. But essentially, ray tracing is all about calculating lights using rays. Ray tracing mimics what happens in the real world. So from a light source, a light is hit to an object and it illuminates the object. Again, from there, it again reflects from the object and hits another object and illuminates that object too, and so on. Essentially, we are doing the same, but in reverse direction. That's ray tracing explained in less than 10 minutes.